Hi, everyone. So I want to finish up the first couple sections of chapter 4, so we can get into the meat of it. And it's in this case more terminology, and then a few kind of fundamental definitions, which serve as good examples, but also are actually going to be useful later. So let me start by talking about something which is not in the text, which is a word that they overlooked, but should not have overlooked, which is axiom. So the book doesn't mention axioms, but it should. Axioms are statements that are asserted to be true and accepted as true for the purposes of constructing a theory. So an example of an axiom is, this is an axiom from Euclidean geometry. It says, given a line L, so here's the line L, and a point P not on the line L, there is exactly one line through P parallel to L. And this axiom has a long and interesting history. So it's stated as a fact, and for thousands of years, it was accepted as a fact, and people wondered whether it was really. It seemed so obvious to them. They felt like the other axioms of Euclidean geometry, like the fact that 2 points determine a line, and other basics like that should be sufficient to imply this axiom. And so it should be possible, instead of having this be an axiom, it should be a theorem following from other results. And it was in the 19th century that a huge breakthrough occurred where actually two mathematicians, more or less simultaneously, a guy named Bolyai and a guy named Lobachevsky, said, well, let's change this axiom. And let's, for example, say that given a line L and a point not on that line, there are infinitely many lines through that point, that point. And in doing so, they invented non-Euclidean geometry. So the thing about axioms is that in ancient times, axioms would have been described as something which is self-evidently true. And in modern times, axioms are described as things which we presume to be true in order to see what's going to happen. And so it's a little bit of a difference in perspective. Just to give you an example of another axiom not in geometry, remember when we talked about set theory, I mentioned that there is a formal notion of set theory, and there's a collection of axioms called the Zermelo-Fraenkel axioms of set theory, which tell you how you can work with sets. And one of their axioms is that there's an empty set. So they call into being the empty set by an axiom. And it's kind of a question in philosophy whether this is whether an axiom is that an empty set exists is a true statement or not. But axioms are true by fiat. That is to say, in a particular theory that we're interested in, we assume the axioms are true, and we see where that gets us. Okay. So what do we rely on in this course as axioms? Well, we take for granted the existence of the integers, the natural numbers, the rational numbers, and the real numbers. We take for granted set theory, or at least naive set theory. We take for granted things like the intersection, the Cartesian product, the union, the set difference. We also take for granted the properties of addition and multiplication, like the commutative and associative laws. All of these things could be viewed as axioms. We don't write them down as axioms, but essentially they're functioning as axioms, as things which we have posited to be true for the purposes of our future work. One axiom I've named closure here, which we haven't been quite explicit about. Closure means that if you take, for instance, that if you take two natural numbers and you do arithmetic on them, the result is again a natural number. In other words, each of the sets, the natural numbers, the real numbers, the rational numbers, and the integers, have the property that if you take the arithmetic operations stay in them. So sums and products of rational numbers are rational. Sums and products of integers are integers. So one way to write this in a fancy way is to say, let x be r, q, z, or n, then given any two elements a and b in x. So that's a quantifier. This says for all a and for all b in x, we have that a plus b is in x and a times b is in x. Notice that we don't necessarily have a minus b is in x and a over b is in x, but at least for sum and product we have closure. And we also take for granted the way greater than or less than works. So we assume these sets are ordered in the way that we usually we think about it. Okay, there's a few other things that we take for granted which can be viewed as axioms, or the book treats them more as definitions, but they're things that we're going to take for granted as true and that you can use whenever you need them. So the first one is the division algorithm. So the division algorithm says, given a, b in the integers, it's important that it's the integers. And again, this is a universal quantifier. This could be written for all a, b in z, such that b is bigger than 0. So maybe a better way to have written this would have been for all a and z and for all b and z bigger than 0. There are unique integers q and r with r between 0 and b so that a equals bq plus r. What is this saying? This is division with remainder. So let's test it out. So suppose a is 41 and b is 7. Then what this is saying is that there's a q and r. R has to be between 0 and strictly less than 7, so that 41 equals 7q plus r. Well, how do you figure those out? Well, you take 41 and you divide it by 7, and you get 5. So 41 is 5 times 7 plus 6. So its quotient is 5 and its remainder is 6. If you like this other notation, you could write it this way. That's the grade school way of doing it. So this satisfies the conditions because the remainder is between 0 and 6, strictly less than 7, and the quotient is 5. And what this is saying is that this is the only way to do this with the remainder between 0 and 7, strictly less than 7. There's no other way to do this. So the remainder is well defined. It's all, you can always, and so you might say, well, can you prove this? And sort of you can prove it, because you can say, okay, let's take 41 and let's start subtracting 7 from it. So 41 minus 7 is 34, minus 7 is 27, minus 7 is 20, minus 7 is 13, minus 7 is 6. So I subtracted 1, 2, 3, 4, 5 7s from 41. And I got 6, and I can't subtract any more 7s from 6 or I would get a negative number, and my remainder is supposed to be bigger than or equal to 0. And this is an algorithm. That's why it's called the division algorithm. An algorithm is a procedure for finding Q and R. And the reason that this is not presented in this way as a theorem is because there's a subtle point here, which that you need to know that you can't have an infinite descending sequence of positive integers. That is to say, you can't take 41 and keep subtracting 7 from it and have it stay positive. That may seem obvious to you, and that's why there's the underlying thing is an axiom. I don't necessarily want to get into this right now, But I do want to do one other example. So we're going to just take this for granted. That's what it means to have an axiom, is that you can do division with remainder and you get a well-defined unique remainder and quotient. You just have to be a little bit careful with negative numbers. What if we take negative 33 and we divide it by 7? So negative 33 is supposed to be something times 7 plus a remainder. But the remainder is supposed to be positive. So in this situation, instead of subtracting 7, we're going to add 7. And we're going to say negative 33 plus 5 times 7, which is 35, is 2. So negative 33 is minus 5 times 7 plus 2. So the quotient is allowed to be negative, but the remainder is, at least if you're using this axiom, the remainder is always supposed to be positive and less than the thing you're dividing by. So this is a little bit confusing because you might say, well, negative 33, when I divide by 7, I should get negative 4, and then there's a remainder of negative 5, right? But that's not allowed. The remainder is supposed to be positive. Quotient can be negative. So division with remainder is one thing we take for granted. The other thing we take for granted is factorization into primes. So if you take the number 33, it's 3 times 11. If you take the number 72, it's 2 times 2 times 2 times 3 times 3. What the fundamental theorem of arithmetic says is that every natural number greater than 1 can be factored into prime numbers. So presumably you believe this. It's often taken for granted in elementary school. And it also says that you can really only do this in one way. That's not really strictly speaking true because you could rearrange the terms here. I could put the 3's and 2's in a different order. But up to reordering, you can only do it one way. So any factorization of 72 into primes is going to have 3 2's and 2 3's. That's called the fundamental theorem of arithmetic. If we did, let's do, how about 112? 112 is 2 times 56, which is 2 times 2 times 28, which is 2 times 2 times 2 times 14, which is 2 times 2 times 2 times 2 times 7. So any factorization of 112 into primes is going to have 4 2's and 1 7. Now, this is not really an axiom. This is really a theorem, and it's proved if you take the elementary number theory course at the very beginning of the class. It takes actually surprisingly not straightforward to prove. But we're going to adopt it as an axiom because proving it is sort of distracting. Interestingly, people didn't really realize it needed to be proved until the 19th century. Gauss, who was a mathematician who lived in the mid-1800s, was the first person to actually feel like it needed to be proved. Before that, it seemed obvious to everybody. And this is another one of these examples of the social structure of mathematics, where something which many people take for granted, then somebody looks at it in a certain way and realizes, okay, I really should prove this. Interestingly, so that's, we're going to take it for granted, we're going to assume it. If you're interested in these things, you could read up more about it. Whereas the division algorithm is close to an axiom. It relies on something which is very directly, which is an axiom called the well-ordering principle. The fundamental theorem of arithmetic is really a theorem, but we're just not going to prove it. We're going to accept it as true. And then a couple more axioms, or definitions, from elementary number theory. The first is divisibility. So we're going to say that A divides B, and we have a notation for it. We write A with a vertical bar B. So this is the symbol on your keyboard, which is the, let's see, it is the shift of above the enter key on my keyboard. It's not the division symbol. It's different from A/B or A/B. It's not one of those. And it's not a number. It's a statement. So saying A divides B, this means that there exists an integer c so that b equals ac. So when I write 14 divides 28, this means that there exists c in z so that 28 equals 14c, and that's true because I can take c equals 2. So when you say a divides b, you're saying that you can solve the equation b equals a times c for some c. Another way of expressing this is to say that b is a multiple of a. So a divides b is the same thing as saying a is a divisor of b, which is the same thing as saying b is a multiple of a. And then two definitions which hopefully you've seen sometime in your life, possibly when you were learning about fractions. The greatest common divisor of integers a and b, which we write GCD of AB, is the largest integer that divides both a and b. So the GCD of 8 and 12 is the largest integer d such that d divides 8 and d divides 12. Well, d in this case, if we can write down the divisors of 8. 1, 2, 4, and 8 are the divisors of 8. And 1, 2, 3, 4, 6, and 12 are the divisors of 12. So the largest number which is a divisor of both is 4. And the least common multiple of two numbers, 8 and 12, this is the smallest integer so that 8 divides d and 12 divides d. In other words, d is a multiple of both 8 and 12. It's a little trickier to do this because we can't list all of the multiples of 8. That's an infinite set. But we can write the first few. So the first few multiples of 8 are 8 times 1, 8 times 2, 8 times 3, 8 times 4, 8 times 5, 8 times 6, 8 times 7, and so on. These are the multiples of 8. And the multiples of 12 are 12, 24, 36, 48, and so on. And you see the smallest common multiple is 24. So the LCM of 8 and 12 is 24. So these definitions will give us something to work with. The greatest common divisor and the least common multiple, divisibility, unique factorization into primes, and quotient and remainder.